We are now ready to begin the conservation law section. There isn't a whole lot that is different in Model 2. Back in Model 1 for the impulse-momentum relationship, we had mv initial plus the sum of the forces times delta t is equal to mv final. This relationship you can derive Newton's second law from. If you bring the mass times the initial velocity over to the other side, you have the sum of the forces times delta t is equal to the mass times this on the other side would be negative. You can pull out the mass and you'd have v final minus v initial. Let's call that delta v. And if you divide by delta t, that would be the sum of the forces is equal to the mass. Delta v over delta t is the acceleration. So the impulse-momentum relationship is related to Newton's second law. And just like we did for Newton's second law in Model 2, we can use this relationship for the x components and for the y components. So we have the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, and the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. So we have something similar here. Instead of using the equation with the vectors, as we have it here, we can do it just for the x components, and it's also true for the y components and the z components. Okay, so you can write just this for your equation, but if it's true for the vectors, it's also true for the components. So because this equation you can derive Newton's second law from, the problems that we solve using the impulse-momentum relationship, you could solve them using Newton's second law, but if they're in this section of the book, you need to solve it using a conservation law. So you can use Newton's second law to check your work, but don't use it to solve problems in the conservation law section. Similarly, on an exam, if I ask you to solve the problem using conservation laws, you have to use either the impulse-momentum relation or the work-energy relation and not Newton's second law. So even though you can solve it that way, you need to know how to solve it using the conservation laws. The impulse-momentum relation is a vector equation. The work-energy relation is not a vector equation. So not much changes for work-energy in Model 2. So you have your velocity squared. So this would be the speed squared, or because the magnitude of the velocity is equal to, if we just have two dimensions, you could say vx squared plus vy squared, which means the velocity squared is equal to vx squared plus vy squared, which is what we have here. It's not the component, it is the magnitude of the velocity squared. So you can write that like we have here, or just v squared, but it's not the component, it's the magnitude of the velocity squared. So that would be vx squared plus vy squared. And then we have the gravitational potential energy. That just depends on the height. Upward is always positive. You have to pick your reference point where the height is equal to 0. It doesn't matter where you pick it, because the only thing that really matters here is the change in gravitational potential energy. And then afterwards we have final kinetic energy, so you'd find that the same way we found initial kinetic energy, but with the speed at event 2. And we have final gravitational potential energy. This term here is going to be different in Model 2. So back in Model 1, we had either cosine of 0 or cosine of 180 because we were working only in one dimension. Here, you can have cosine of any angle, and that is the angle between the force vector, the net force, and the displacement. Or, for any force that you have, if you break it down into components, then any component of that force, when you look at the angle between that component and the displacement, would either be 0, 90, 180, or 270. So if you break the force down into components, then your only choices would be its cosine of 0 degrees, which is equal to 1, cosine of 90 degrees, which is equal to 0, cosine of 180 degrees, which is equal to -1, or cosine of 270 degrees, which is equal to 0. So you don't have to break the force down into components, but if you do break the force down into components, then any component which is perpendicular to the displacement vector does no work. So if the component of the force is going in the same direction as the displacement vector, you get 1. If it's going in the opposite direction, then that force or that component of the force does negative work. And if the force is perpendicular to the displacement, the force does no work. So one example of that would be if you're pushing something on a surface. So let's say that you have a crate on a surface and you're pushing this way. It's a horizontal surface. You have the force of gravity acting downward. You have the normal force acting upward. If the box is moving horizontally, you got your displacement vector here. The normal force is perpendicular to the displacement, so the normal force does no work. The force of gravity is perpendicular to the displacement, so in this case, the normal force and the force of gravity would do no work because they are perpendicular to the displacement. If you had a rope attached to the block and the rope was going at some angle, and let's say the crate is still moving on the floor horizontally, you could use the angle between the displacement and the rope would be this angle here. So you could use this angle, or you could break the force of the rope down into components. So those would be the components. This is the x component. For the x component, the angle would be 0, and for cosine of the angle, you would have 1. And for the y component, the angle is 90 and you would get 0, so only the x component does work and the y component does not do work. But instead of breaking it up into components, you could instead just do the force of the rope times delta r times cosine of the angle here. Okay, so we will see how that works when we do some example problems.